Okay, so we did BH3 and CCl4. You've got to be able to do all of those. In terms of the shape, if you want to get a head start on the shapes, basically what happens is all these lone pairs and bond pairs, they are all electrons, and so what they do is they repel each other. So you just draw them as far away from each other as you can. You know, if there's 3, draw them in a triangle as far away as possible. If there's 4, now they're actually going to be 3-dimensional, so they're going to form a tetrahedral shape, but we'll do that when we do shapes. But for now, if you want to draw them anywhere near close to what they're going to be, just draw them as far away from each other, from themselves as possible. Okay, Banza, remember I spoke to you last session about me being worried about you. I'm worried when you're looking other places when I'm talking to you. What you should have now is you should have your notes that I gave you. And you should be, most of the stuff's done on them, and anything missing, you should be fixing them. You know, where's yours? Okay, then you've got the right thing, you've got paper, and you write everything. Good. So we move on. Chlorine diox, fluorine oxide. Okay, kind of like difluorine oxide or fluorine oxide. How do you think that's going to bond? Same as what? Same as? With hydrogen, which was called? H2O, which is? Water. Theoretical chemistry is your thing, eh? So what's going to happen is you're going to have that. 2 fluorines are going to join with oxygen, and they're each going to share 1 electron with it. And here you're going to have 1 bond there and 1 bond there, and you're going to have OF2, the same as we had H2O. Why do we put the O in front of the F? Why don't I say F2O instead of OF2? Well, you'll get to know what happens there. Basically, if you want the sort of primary school answer, the primary school answer is if the thing is on the left of the other thing on the periodic table, then we put it on the left in the name. So look here, hydrogen's here, oxygen's there. When hydrogen bonds with oxygen, we say H2O. But oxygen's on the left of fluorine. So when oxygen bonds with fluorine, we say OF2. That's the real reason is because the things on the right are more electronegative. Now, I haven't even told you what that means yet, but you'll find out what that means. You always put the most electronegative thing last. So if it is on the left of it on the periodic table, then you put it first. Okay, so that's OF2. There's your oxygen atom, and there's your Cooper structure. Lewis structure and Cooper structure. Please draw both of them. Mr. Ridgway, please draw both of them. All right. Yeah, that's fine. Yeah, just some of my slides I've printed both. Don't ask me why. Okay, so the pairing, they've both got full outer shells now. Both of these got 8 and these got 8, but one of them is one that they're borrowing. All right. So, can I move on? All right. So the thing now, boron trifluoride. Okay, the trifluoride is giving you a hint. Boron has got how many electrons? 3. How do we know it's got 3? Because it's in group 3. So if boron's got 3 and each fluorine needs 1, you can have 3 fluorines bonding with the 1 boron. What do you mean? In that shape? Because remember I said to you, they repel and they're going to go as far away as possible. But you don't have to draw it like that. So who's this? All you've written down is moon.
Yes, I'm moon.
You are moon.
That's my name's Cameron.
You prefer moon.
I don't really mind.
So I can call you moon. Okay. I think I prefer Cameron. Cameron, you don't have to draw it like this. You can draw it one there, one there, one there. You can draw them in 90 degrees if you want. When we come to draw the shape, when I ask you to draw the shape of it, then you'll have to. In fact, we seldom ask you to draw the shape. We normally ask you to name the shape because the shapes are 3-dimensional and you can't really draw them properly.
So there's supposed to be another electron.
Yes, there is. So I just wanted to check, Cameron, that when you said you are moon, you're not actually identifying as the moon. Okay.
I consider myself a moon.
Right. Because I often use a little example in my class of, you know, when we're speaking rubbish, if we know we're speaking rubbish, it's fine. If we don't know we're speaking rubbish, it's not fine. So I often use the example, you know, if your mate walks up to you and says, oh, hey, I'm Spider-Man. If he knows he's messing about and he's not actually Spider-Man, it's fine. But if he really believes that he's Spider-Man, then you've got a problem. Okay. So I just want to know. Right, can I move? Good. PCl3. Right? We're still busy. Okay, keep going. Why didn't you keep up today? Go. Cool. PCl3. Done for you. It's dead easy. SF6. Now, here's the problem. PCl3 is fine because phosphorus has got 5 valence electrons. We know that because it's in group 5. It's phosphorus trichloride. Okay, so you can see here phosphorus is in group 5. We know therefore it's got 5 valence electrons, 1, 2, 3, 4, 5. It's very similar to nitrogen. That's why we put them in the same group. Nitrogen's there, phosphorus is there, same valence electrons. And so it's going to share one with each chlorine. Now I'm telling you that there's a compound called SF6, sulfur hexafluoride. How on earth can that happen? Because sulfur is in group 6. So it's got 6 valence electrons, but aren't they in pairs? It wouldn't be ionized.
No, they're looking at the
Nice guess, but it wouldn't be. So how does SF6 work? Well, what happens is this. When it comes to bonding, almost anything goes. The one rule that is almost never broken is that electrons all have to be in pairs. But the other rules, some of the other rules are more like guidelines. So remember you were told, oh, there's a maximum in the shell of 8. Yeah. Only when there is more than that. Okay, there are times when there can be more than 8. So that's not a hard and fast rule. Okay, it's more like a guideline. So SF6 is one of the few molecules that we know of that breaks that mold. So what happens to SF6 is this. Sulfur, all right, there's his 6 electrons. The black one's there, 1, 2, 3, 4, 5, 6. That's sulfur's valence electrons. They all bond individually with 1 fluorine, with making 1 covalent bond. And then you get 6 covalent bonds around the sulfur.
sulfur was by itself. There would be no pairs. If it wasn't bonded.
No, it would have had pairs. So if you were going to draw sulfur, right? If I said to you, draw sulfur's Lewis diagram, you know, before it's bonded. I'll do this. Let's go pen. Normally you would have done this. You would have gone, okay, sulfur, 1 electron, 2, 3, 4, 5, 6. Normally we would have drawn it like that. And then said, oh, it's only got a valency of 2, minus 2. Because what are the valency of compounds in group 6? Minus 2. But for SF6, it changes. And it's one of the exceptions you just have to learn. So if you're going to draw the Cooper structure, you would now draw that. 1 sulfur with 6 fluorines around it. Now I know that's looking quite hectic and quite congested. The word I'm looking for, quite congested. But you'll see when we come to shapes, there's actually a way that it fits nicely. Say that again. Okay, so it hasn't got 3 in its outer shell. Sulfur's actually got 6 in its outer shell. You can see them there. But where are you getting 3 from? No, it would only need 2. Normally we would say, look, sulfur's got 1, 2, 3, 4, 5, 6. It's only got 2 vacancies because remember that we said before a full shell was 8. Yeah. So it actually only needs 2. This is just what it does. Yeah, it just does. I'll come to you in a second. If you ask me the reason it does, the only thing I can say to you is it's the lowest energy structure. That's what is the guiding principle for everything that happens.
Sulfur bond with just 2 fluorine.
Not with just 2 fluorines, no. I suspect one of the reasons is because fluorine's attraction on electrons is so strong. It would probably take those electrons away completely. Yeah.
It's a sulfur could bond with something else that has
2, yeah. So, for example, if sulfur bonds with a metal, then what it does, sulfur takes 2 electrons from the metal, becomes S2 minus. That's a sulfide ion, and you get like sodium sulfide.
Like hydrogen.
Yeah, hydrogen sulfide. Yeah. So that can, yeah, question. Could it bond like that with 6 hydrogens? Theoretically, yes. It doesn't though, because with hydrogen, sulfur makes H2S. So it just bonds with the 2. Why? The only thing I'm going to tell you is because it's the lower energy structure. I don't actually know. That's the reason. Why it's the lowest energy structure, I don't know. Now you wrote on here Newt. That's what you want me to call you. Newt. Okay, Newt. There we go. Right, can I move off this? Can I move off this? PCl5. Yeah. What's this called? This is called phosphorus pentachloride. Phosphorus pentachloride. Why is this giving me the option to give control to somebody else? I don't want to see that. Anyway, phosphorus pentachloride. So you can see what's going to happen. Phosphorus is in group 5. Normally we would have said it's got a valency of 3, but now when it bonds with certain things, it's available to bond with all 5 electrons. So exactly like sulfur hexafluoride, you're going to get 5 chlorines all around the phosphorus, each bonding with 1 electron, and you've got PCl5. Question to Mo. Yeah, so what I'm doing there is I'm drawing, bless you, brother. I'm already bringing shapes into it just because I know its shape. Draw it like that for now. I'll explain the shape later when we do shapes. If you want to just draw them like, you know, if you want to draw it like this, it's fine as well. So this I got my new laptop today, and it's battling a little bit because it's never been pushed so hard before. If you want to draw it like this, 1, 2, 3, 4, 5, that's also fine.
Actual shape, if you're asking the question, would be the.
Yeah, the actual shape will be that. Because I'm drawing, that's actually in 3 dimensions. Yeah. Yes. So I'm drawing like this because this is it in 3 dimensions. When we've done shapes, it'll make sense. But I don't want to go there now. Happy?
So what is this one?
Sorry?
What is this one?
So that I've drawn, you can ignore it for now. We'll go there. Okay, so F-power diagrams. Yeah, all I'm showing here is why, you know, this business of when you draw or when we draw these atoms, and I say to you, okay, now, you know, nitrogen has got a valency of 3, and I'm drawing the 5 electrons around the nitrogen like that. You might think, well, why are you drawing them like that? Right? If you think back to last year when you did the F-power diagrams, you know, 1s1, 2s2, 2p3, you would have done things like this. So you got 1s1, 2s2, 2p, 1, 2, 3, and you put the electrons in from the bottom. 1 goes there, 2 there, 3, 4, then 5, 6, 7. So if you did nitrogen, for example, this would have been nitrogen's structure. 1, 2, 3, 4, 5, 6, 7. And it actually looks like this. 2 are paired in that outer shell. 2 are paired and 3 aren't paired. Do you agree? So it just turns out if you do the electrons like this and you put them in 1, 1, 1, 1, and then you start pairing them up, it kind of mirrors the actual electronic structure in the outer shell for most configurations. So that's why we do it like this. When we do the Lewis diagram, you put the symbol in the middle, you start with electrons singly, 1, 2, 3, 4, and then you go 5, 6, 7, 8. And for most atoms, that will give you a structure around here, which is pretty close to what's actually happening. Except in the exceptional cases like SF6 or PCl5. All right, that's all I'm trying to show you on that slide. Okay, so now we're going to start doing a few ions. So how do these work? Compound ions. NO3. Now you know what an NO3 is. It's a nitrate ion. You've had that in your valency diagram since you were in grade 9, in your valency table. Remember? Carbonate ions, sulfate ions. So how does NO3 minus work? You've got oxygen. There's oxygen's electronic structure. 1, 2, 3, 4, 5, 6. We know it's got a valency of 2. Here's nitrogens. Now to try and figure that out just from your head, you're not gonna get it. Even for me, what I have to do with these, I know what it is and then I draw it. Okay, and I don't think there's a shorter way around it. I can't explain to you how to work this out. You just have to learn it. So I might as well show you. What happens is this. Now, these circles that I've put around here, you can ignore. Okay, that was the old-fashioned way of doing it. We don't use those circles anymore. Watch what I've got. Here's the nitrogen in the middle. So let me explain it, and then you can draw it. So watch me explain it first, then you can draw it. Here's the nitrogen in the middle. Where's these 5 electrons? There's 2 there, 3, 4, 5. 1, 2, 3, 4, 5. How do I know they're like that? Just because I've learned. Question.
So the one thing drawn in red is that.
I'll come to you in a minute. I'll explain that in a minute. That's the spare one. Yeah. Now here's 3 oxygens. Now you know there's 3 because it's NO3. So here's 3 oxygens. Each oxygen should have 6 electrons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. There's an oxygen. 1, 2, 3, 4, 5, 6. That explains all the electrons except this one here, this red one. So where does he come from? We don't know. He came from somewhere. Could have been from a hydrogen, could have been from a metal, could have been from, but that electron. Yeah.
Every time.
So, well, so it happens often because you can't go and buy, listen, you can't go and buy a bottle of NO3 minus. You can't get NO3 minus on its own. If you could buy a bottle of stuff where every particle in it had a negative charge, the amount of stuff, any amount of stuff that's big enough to see, would have so many negative charges that it would be so reactive that if you went anywhere near it, it would shock you, steal its, get rid of that extra charge and be neutral. Okay. The only way you can get NO3 minus is by having something like this. You'd need, where am I? Yeah, you need something to balance off that negative charge. HNO3 minus, where the H is positive and the NO3 is minus. Where did that little extra electron come from in this case then? From the hydrogen. Okay, so that's an ionic compound. It has stolen an electron from somewhere, and so that's where that extra electron came from. You don't have to worry about where it came from, you just need to know that it has to be there. And you know it has to be there because up here it says NO3 minus. Yes, Thomas.
Right, so could HNO3 minus bond?
HNO3 minus couldn't bond. H plus and NO3 minus can bond.
How would you do that?
I'll show you in a minute. I'll show you in a minute. So the nitrogen is making a double bond here with this oxygen. It's making a double bond here with this oxygen. And then it's making a single bond with this oxygen. And then this oxygen has got the extra electron. Okay. So there, double bond there, single bond here. And this oxygen has an extra electron. That's why it is minus. And here I'm showing that it could actually bond, that oxygen couldn't bond to make HNO3, which would be this reaction at the bottom here. NO3 minus plus H plus goes to form HNO3. And that's nitric acid. And you guys learned about nitric acid in grade 9. Okay. So that's the nitrate anion. And from today, you must understand it and be able to draw it. Have you got it there, David? Hang on a second. Have you drawn it? Okay. Yes, sorry? No. No, if we ask you to draw the nitrate ion, you just draw this thing here with the brackets and the minus. Yes, Thomas.
So what are the 2 dots for?
Which 2 dots? These here. Those are to show you the lone pair that's on there, but you actually don't have to draw them. You just draw the minus here. Okay. In the Cooper diagrams, we don't draw the lone pair. All right. All got it? Lekker. Now, let's go and have a look at CO3 2 minus. Anybody want to try and chance it and do it on your own? Great start. Okay, so this one I did using the laptop. So let's have a look. This time I've drawn the carbon's electrons as crosses. It doesn't matter who's the cross and who's the dot. 1, 2, 3, 4. We know carbon's got 4 valence electrons, that's fine. It makes a double bond with 1 oxygen. Then it makes 2 single bonds with 2 other oxygens. And those 2 other oxygens have each got an extra electron. So let me just go here. Annotations. And I want to change this. I'm going to make one of these red. And I'm going to make one of these okies red. And that's why this thing is 2 minus. Okay, so now you don't have to show, you guys don't have to show those electrons are separate or are different. Because in truth, we don't know whose electrons belong to who. So in truth, we don't know which of those electrons come from somewhere else or which don't. It'd be like you trying to figure out which are your fleas and which fleas came from the dog. Fleas are fleas. Okay. What's what? Carbonate ion. You should know that, Mo. Since grade 9 in your valency table, you should have known that CO3 2 minus is carbonate. The other one was nitrate. So, gentlemen, listen, I'm getting a little bit worried here because a few of these guys are making me think that you guys haven't actually learned your valency table. Now, let me just help you here. If you go and have a look at my very useful class website, and you go down here, there's a page that says TLR. See that? If you go on TLR and you go down even further, No, flip. Where is it? 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 There's a thing here that says, oh no, it's not there. It's under here. More. Yeah, you see here? It says valency table. This valency table is the same as the one on the grade 9 intranet page. And you should have known this since grade 9 when we did writing formula. If you didn't learn it, or if you don't know it out of the top of your head, and by know it out of the top of your head, I mean, if I say dichromate, you must know Cr2O7 2 minus. Okay, now, don't come and pretend to me that you are serious about your science if you don't know that table out of your head. If you're serious about, you cannot, let me tell you this, you can't do chemistry if you don't know that table. Okay? You have to know it. Now, I've made it easier for you. The ones in yellow, you don't actually have to learn because their valencies you get from their groups. So why is aluminium 3+? It's in group 3. Why is their valency 2? They're in group 2. All right? Those you don't have to learn. Here as well, fluoride, chloride, bromide, iodide, they're all in group 7. So their valency is -1. Because remember, the rule is for non-metals, the valency is 8 minus the group number, or the group number minus 8. Why is oxygen and sulfide, why are they 2 minus? Because they're in group 6. The only ones you have to learn are the ones in white. The ones in blue, we will always tell you. Because copper can be 1+ or 2+. So how do you know if it's copper 1 or copper 2? We'll tell you. This is copper 1 oxide, or this is copper 2 oxide. And here's a little hint. If we don't tell you, and you're not sure, then go for the 2. The 2 is normally the most stable, if there's 2 possibilities. So the only ones you have to learn are the white ones. Silver, oxonium, that's supposed to be, is cobalt, zinc, lead, these, hydroxide, nitrate, nitrite. There's a difference between nitrate and nitrite. Eh? Nitrate and nitrite. I've got a daft little story about that if you're interested. Interested? Yes. So many years ago, I was at Bible college, and there was a guy there whose name was George. George was Chinese. I'm not sure if he was from, if he spoke Cantonese. I'm not sure what dialect of Chinese he spoke. But I said to him, how do you say Chinese? Because I try to make him feel, you know, at home. And normally if you speak to somebody in their language, they feel more at home. So I said to George, how do you say hello in Chinese? So he says, oh, Chinese, very easy, very easy. I'm not going, he says, no grammar. No grammar in Chinese. Said, what do you mean there's no grammar? No, it's like in English, you've got 1 table, 2 tables. Chinese is just the same. That's why when they say English, they often say 2 tables. They don't say tables. Because in Chinese, there's no grammar. So I'm like, geez, that's fantastic. He says, yeah, easy, easy. Just one thing you have to remember. So I'm like, what? He says, soy, soy, soy. I'm like, what? Soy means something. Soy means something else. Soy means something completely different. What do you mean? So he says, soy, soy, soy. The inflection. Inflection. Anybody speak Chinese? Cantonese or Mandarin? And the 3 different inflections mean something completely different. So like the one, soy is grandmother, soy is a horse. They mean something completely different. So I'm like, are you serious? Every single word has got 3 different sounds that sound to me exactly the same, but they mean 3 completely different things. And you saying this is easy? Anyway, nitrate, I think is lower. Nitrate, nitrite. The lower one always has the bigger number. Sulfate, sulfite. Sulfate, SO4 2 minus, sulfite, SO3 2 minus. Nitrate, nitrite. Anyway, if it helps you, fine. If it doesn't, just learn it. How are we doing for time? 5 minutes.